Hi, my name is Leo Millet, and in my presentation, I'll be talking about who I consider to be the most renowned math hobbyist, or Pierre de Fermat. Mathematics is one of the least popular subjects of learning for students. Many mathematicians in history have worked and studied their entire lives to expand and expound a small niche among math at large. Only a select few are able to break ground in various different areas of mathematics. The French mathematician Pierre de Fermat is one of those rare individuals. His study and discoveries came as he devoted his life to a different profession in the French justice system. Fermat had discoveries and impacts in the areas of number theory, probability, calculus before Newton, and a simple theorem that remained unproven until the late 20th century. Pierre de Fermat was born between 1601 and 1607 in the town of Beaumont-de-Lamont. He was born to Claire de Long and Dominique Fermat. His mother came from a line of parliamentary judges, which likely impacted his decision to study law in Toulouse. Fermat worked in law throughout his entire life, his final position being that of King's Councillorship in the local parliament of Toulouse, a position which he held until he died. It is interesting to note that Fermat's life is often described as quiet, stable, and uneventful. Technically, since Fermat worked his entire life in the court system in France, instead of working in math, he would be considered an amateur mathematician. It is interesting to see that he was able to have such a large influence over many different areas of mathematics while putting in strenuous years into his primary career. His position enabled him to minimize his unofficial contacts in order to avoid the temptations of bribery and other corruption. Math possibly offered a much-needed break. Many of his mathematical discoveries were proposed in letters to others, and very little of his work was published in his own lifetime. Fermat could be considered the prince of amateurs and the greatest math hobbyist of all time. We'll start by talking about Fermat's impact in number theory, or the study of the properties of integers. This dive into number theory was inspired by a 1621 edition of Arithmetic by Diophantus. One of his discoveries captures an interesting property of a smaller group within the prime numbers. For the sake of clarity, we define prime numbers as follows. A prime is a positive whole number whose factors are limited to only one in itself. Fermat discovered that all primes that could be expressed in the form 4n plus 1 could also be expressed as a sum of two squares, with n being a positive whole number. A few examples are shown here. For n equals 1, 5 is equal to 1 squared plus 2 squared, or 4 times 1 plus 1. 41, which is a prime, is equal to 4 squared plus 5 squared, or 4 times 10 plus 1. Fermat also developed a technique to demonstrate some of his theorems called infinite descent. This technique parallels the technique of a proof by contradiction, in which some mathematical expression is supposed to be true through manipulation and some exploration. A contradiction based on the original assumption is discovered, showing that the original assumption was in fact false. In infinite descent, some sort of expression is assumed, and what logically follows through manipulation is a process that can be hypothetically repeated infinitely. However, if this process or manipulation was actually done infinitely, it would break a part of the original assumption, thus leading to a contradiction and the assumption to be decided as false. Both proofs by contradiction and infinite descent find a contradiction in math or logic. In fact, you could classify infinite descent as a type of proof by contradiction. To demonstrate Fermat's technique of infinite descent, we will show or prove that the square root of 2 is irrational. We'll need a couple definitions. The first one, that being a rational number, is one who can be represented as a over b, with a and b being integers and b not equal to 0. Also, a number a is even if it can be written of the form a equals 2x, where x is an integer. A number a is odd if it can be written of the form a equals 2x plus 1, where x is an integer. We will prove this by starting with supposing that the square root of 2 is rational. Thus, by our definitions, we can represent the square root of 2 as equal to a over b. By squaring both sides, we get 2 equals a squared over b squared. And by some algebra, we get 2 times b squared equals a squared. Thus, a squared is even, and from example 3.1 in the book, we know that a is even too. Since a is even, we can write it as a equals 2c for some c in the integers. By substitution, we get the following. 2b squared equals 2c quantity squared. Then 2b squared equals 4c squared. Thus, dividing by 2 shows us that b squared and b are even. We can continuously represent a and b as smaller and smaller numbers, even numbers, infinitely. This is impossible since you will always reach a number that is not divisible by 2, no matter how large of integers you start with. Therefore, the square root of 2 is irrational. Fermat shares his name with a few of his mathematical discoveries, one of which is known as Fermat's little theorem or Fermat's lesser theorem. A couple definitions are necessary to proceed. For two integers m and n, we say that m divides n, or m divides n, if and only if n equals m times k, for some k in the integers. Two integers, a and b, are said to be relatively prime, if and only if the largest natural number that divides a and b is 1. This can be expressed notation-wise as close parentheses around a comma b is equal to 1. 1 in this case is the greatest common divisor of integers a and b, or the largest natural number that divides a and b. Fermat's little theorem is as follows. For any prime number p, an integer a, such that a and p are relatively prime, he divides a to the p minus a. Suppose we did not know whether or not our p was prime. Any prime number satisfies this theorem. So would this theorem be a good test to determine if a number is prime? Consider a equals 2 and p equals 341. 341 appears to be prime, and we note that 2 does not divide 341, and yet 341 divides 2 to the power of 341 minus 2. Yet 341 is not a prime. We can get 341 by multiplying 11 by 31. Thus, all primes satisfy Fermat's little theorem, but primes do not exclusively satisfy the theorem as well. Another contribution to number theory that bears Fermat's name is the concept of numbers of Fermat. In 1640, Fermat sent letters with an idea to his group of thinkers, including Blaise Pascal and Marin Mersenne, proposing that numbers that can be expressed in the form 2 to the power of 2 to the power of n plus 1, then in the natural numbers, are always prime. Fermat showed this to be true for n equals 1, 2, 3, and 4. This was believed to hold for all natural numbers until around 1740, when Euler showed that 2 to the power of 2 to the power of 5 plus 1 has a factor of 641. Thus, even among Fermat's many achievements, a few mistakes can be found. Fermat's most famous theorem falls into the realm of number theory. This section will only serve as an introduction, while the full implications and story behind this theorem will be presented later. In the margin of Diophantus's Arithmetica, Fermat wrote, on the other hand, it is impossible to separate a cube into two cubes, or biquadrate into two biquadrates, or generally any power except a square into two powers with the same exponent. I have discovered a truly marvelous proof of this, which, however, the margin is not large enough to contain. In our notation today, we would write this as the equation x to the power of n plus y to the power n equals z to the power of n has no integer solutions for n greater than 2. In other words, there are no integers x, y, and z such that x to the power of n plus y to the power of n equals z power of n for n greater than 2. This is an example of the Diophantine equation, or a polynomial equation with integer coefficients, of which we are only interested in finding the solutions, if they exist, that are integers. First glance, this may appear to be superficial or something that can be easily explained away. Nobody, including Fermat himself, would have been able to guess the time and lengths numerous individuals would take working on this simple conjecture. Now we'll talk about Fermat's impact in probability. Probability is a branch of mathematics that concerns the likelihood of events occurring. Fermat is considered to be one of the joint founders of the theory of probability alongside Blaise Pascal. This field of math can trace its roots to a question proposed to Pascal by Chevalier de Mier about distributing the points of an unfinished game. Through correspondence of letters, both Fermat and Pascal arrived at the same answer to the problem despite using different methods. A generalization of the question, along with Fermat's explanation, will be presented here. The question Fermat and Pascal asked or addressed was, how would one distribute the points or stakes of an unfinished game of chance if the partial scores of the players are known? They both considered the most important factor to be the number of rounds each player needed to win to achieve overall victory. Fermat reasoned that if player 1 needed to win another R rounds to win overall, and player 2 needed S more rounds, either player could have won an R plus S minus 1 rounds. We note that either player could win in less rounds, but we can also consider that both players agreed to play the remaining round without stakes. With R plus S minus 1 rounds, there are 2 to the power of R plus S minus 1 possible outcomes. The reason for this relies on the principle of counting. Suppose we have a process called P with k many steps that can be ordered step 1 through step k. Also suppose that each step has n many ways that it can be accomplished. For example, step 1 has n1 options and step k has n to the k many options. The number of ways our process P can be accomplished is the product of all possible outcomes for each step, or n1 times n2 all the way to multiplied by nk. In our case, each round has two possible outcomes. Either player would have to win, and we have r plus s minus 1 rounds. The total possible outcomes would be the product of an r plus s minus 1 number of 2's, or 2 to the power of r plus s minus 1. Fermat then calculated all the possible outcomes and counted how many contributed to each player winning. One of the core aspects of modern-day calculus is the idea of calculating the tangent line to a given curve. Fermat was born roughly 40 years before Isaac Newton and Gottfried Wilhelm Leibniz, the fathers of modern-day calculus. Fermat himself had an idea about this concept of the tangent line. Fermat's idea was about a special property of the tangent line. That is, the tangent line has a special property in that it intersects the curve at only one point. One key concept to Fermat's idea is the concept of slope, the rise over run of a line, or its steepness. Fermat's technique for determining the tangent line involves determining the slope of a line that intersects a known curve at a given point. For a given curve, y equals x squared, in the point 2, 4, we begin by using the point slope form of a line, or y minus y1 equals m, or the slope times x minus x1. We substitute our known point in to be y minus 4 times m times x minus 2. We then solve for y. We equate our two expressions to get x squared plus 4, or x squared equals 4 plus m times x minus 2. We now multiply this out to get a quadratic polynomial. This polynomial can be solved by using the quadratic formula. We end up with the expression here, x equals m plus or minus m minus 4 over 2. To end up with only a singular solution, we set m equals 4 equal to 0, giving us a slope of 4. Thus, the equation of our tangent line y equals x at 2, 4 is y minus 4 equals 4 times x minus 2. We can check this using our modern techniques for calculating derivatives. Using the power rule, we can take the derivative of y equals x squared to get y prime equals 2x. This equation represents the slope of our original equation equals y equals x squared. Thus, we plug in our x coordinate 2 to get y prime times y prime equals 2 times 2, or y prime equals 4. Thus, the slope of our tangent line of y equals x squared and x equals 2 is 4. We now return to our discussion of Fermat's famous last theorem. We restate the theorem as the equation. X to the power of n plus y to the power of n equals e to the power of n has no integer solutions for n greater than 2. Fermat himself proved this theorem for n equals 4 using his method of infinite descent. We will work through that proof here. A few definitions and theorems will be presented preceding the proof. So we start by defining x, y, and z to be a primitive Pythagorean triple, where x, y, and z are solutions to the Pythagorean formula, can be expressed in the following way. X equals 2pq, y equals p squared minus q, and z equals p squared plus q squared, where p and q are relatively prime positive integers. P is always greater than q, and only one of p and q is even. Also, if an integer n is even, then n squared is even. If an integer m is odd, m squared is odd. Finally, if an integer m is even and an integer n is odd, then m plus n is odd. Couple more. Let n be greater than 1, be a natural number, positive whole number. There exist primes, p1, p2, all the way to pk, and natural numbers a1, a2 to ak, such that n equals p to the power of 1, p1 to the power of a1 times p2 to the power of a2, all the way multiplied by pk to the power of ak. This product of primes is said to be the prime factorization of n. Finally, let a and b be natural numbers, and suppose that a equals q times b plus r for some q and r into the natural numbers. Then the greatest common divisor of a and b equals the greatest common divisor of b and r. We show our proof for n equals 4 of Fermat's last theorem here. Suppose there are integer solutions to the equation x to the power of 4 plus y to the power of 4 equals z to the power of 4. Suppose now that x, y, and z are integer sides of a right triangle with a square area. This means the area of the triangle can be expressed as the square of some integer. We divide x, y, and z by any common factors to show that this triangle is indeed primitive. By the definition of primitive Pythagorean triples, we can say the following. X equals 2pq, y equals p squared minus q squared, and z equals p squared plus q squared. In this, we note that p and q are relatively prime positive integers. P is greater than q, and only one of p and q is even. We also note the area of our triangle, 1/2 base times height, can be expressed as 1/2 xy or pq times p squared minus q squared. Since the area of our triangle is square, we could say that p squared times p minus q times p plus q equals n squared for some integer n. Since the right-hand side of the equation is a square, so is the left-hand side, and all of the factors are as well. This can be shown by taking advantage of the concepts of relatively prime terms and the definition of prime factorization, both implying that each term is in fact a square. We now defined R and S to be R squared equals P minus Q and S squared equals P plus Q. Since by definition we know that one of P and Q is even, the other must be odd. Hence R minus S and R plus S are even, where one is divisible by 4. We now define U and V to be U equals R minus S over 2 and V is equal to R plus S over 2. We also note that U squared plus V squared equals R squared plus S squared over 2, which is equal to P is squared. This makes U and V another set of legs belonging to a primitive Pythagorean triangle, whose area is U over V, U V over 2 is equal to Q over 4. Since Q is a square and U times V is even, we know that Q over 4 is square. Thus, we have another triangle with primitive Pythagorean sides and a square area. This process can be continued infinitely. However, this is a contradiction. Since we are working with integers, we will reach a point where this process is no longer possible. Therefore, there are no integer solutions to the equation x to the fourth plus y to the fourth equals z to the fourth. Fermat also noted that only prime powers would need to be considered, since if an answer existed for a power of n, it would also exist for any power multiple of n. Other mathematicians proved other various powers of n as well. Sophie Germain proved Fermat's theorem for n less than 100. There was also monetary incentive for proving Fermat's last theorem as well. In 1815 and 1860, the French Academy of Sciences offered a gold medal and 300 francs to anyone who could produce a proof. And in 1908, the German Academy of Sciences offered 100,000 marks for the same end. Both awards brought in numerous attempts, yet none stood up to scrutiny. Other advancements in math occurred as the years ticked by without a proof. Non-Euclidean geometry was theorized and developed. It was during the mid to late 1900s that the idea of elliptic curves began to be thought about. Elliptic curves are cubic polynomials in two variables. For example, y squared equals ax to the power of 3 plus bx squared plus cx, where a, b, and c are integers or rational numbers. Separate from this, in number theory at large, was developed the idea of modular forms. The simplest description of modular forms are that they are functions that repeat endlessly on the complex plane. In 1965, Goro Shimura, a researcher at Princeton, developed a conjecture that would be key for finally proving Fermat's last theorem. In its simplest terms, if a bridge could be built between number theories, elliptic curves, and modular forms, then Fermat's last theorem could be proven. Around 1968, Ken Ribet, a professor at the University of California at Berkeley, formulated and proved a theorem which established as fact if the Shimura-Taniyama conjecture was true, then Fermat's last theorem would fall out as a direct consequence. All that was needed now was someone with the required mathematical knowledge, determination, and perhaps madness necessary to prove it. Andrew Wiles had a dream since he was 10 years old to prove Fermat's last theorem. It wasn't until some of the more recent discoveries that Wiles began to believe that his dream could be accomplished. From that time on, Wiles began a 7-year journey that he described as stumbling through a dark mansion that slowly became illuminated. On Wednesday, June 23, 1994, Wiles concluded what had been a 3-day presentation with And this proves Fermat's last theorem. After an error was discovered, it took until May 1995 for Wiles to work through this error and publish a correct proof. Andrew Wiles' proof of Fermat's last theorem is beyond most students and even professors' highest mathematical comprehension. However, a simplistic version of it will be given here. The Diophantine equation, x to the power of n plus y to the power of n equals z to the power of n, can be translated into an elliptic curve. That curve can be represented as a certain modular form known as a torus. Taniyama and later Shimura suggested a connection between elliptic curves in Euclidean geometry and corresponding structures in the non-Euclidean plane. Gerhard Frey suggested a connection between elliptic curves, Fermat's last theorem, and problems that would arise if there were solutions to Fermat's theorem. Wiles, accepting Reidit's proof, found that he could prove Shimura's connection by counting the Euclidean elliptic curves and their corresponding non-Euclidean counterparts to demonstrate a one-to-one correspondence between the two groups. It took around 300 years, the discovery of many different branches of mathematics, and the invention of computers for proof of Fermat's last theorem to be found. The question to be asked now is, did Fermat actually possess proof when he scribbled down that note? Andrew Wiles believed that Fermat did not possess a proof, at least not a correct proof. Wiles also said that Fermat could not have possibly had this proof in mind when he wrote his famous note in the margin. Wiles' proof is a 20th century proof. Despite opinions either way, the truth will most likely never be known. Fermat's contributions to the field of mathematics had a wide and far-reaching impact. The modern-day mathematics student cannot go a semester without touching on a concept studied and expanded by him. There is no way Fermat would have or could have imagined the lasting impact his work would have had into the future. Pierre de Fermat is an example to the modern-day student to find what they love and do it. Work at it, even if you do something completely different with your life. The pursuit of that dream can have boundless future applications. These are the sources I use in this presentation, and thank you for your time.